A 2,000-year-old temple stands untouched after a massive earthquake shatters a modern city nearby. This is not a rare miracle, but a documented pattern across the world's most active fault lines. Why do ancient stone structures, built without computers or seismographs, consistently resist earthquakes better than our advanced steel and concrete buildings? Today, you will discover the forgotten engineering secrets that gave our ancestors this incredible advantage. We will uncover how interlocking stones and mystical mortars created flexible, living buildings, and reveal the single biggest mistake modern construction makes in its fight against nature's power. What does it truly mean to build something that lasts for millennia? A 2,500-year-old temple in Kathmandu remained perfectly intact after the 2015 Gorkha earthquake, while modern apartments and offices nearby crumbled into dust. This same story repeated itself in Peru, in Turkey, and in Japan. It forms a great and puzzling contradiction, a seismic paradox that challenges our very definition of progress. We design buildings with sophisticated computer models and advanced materials, yet structures erected with nothing more than chisels and human labor routinely outlast them. How could civilizations that knew nothing of tectonic plates or seismic waves build with such profound foresight? The answer is not that they were lucky. It is that they were brilliant in ways we have forgotten. Structural engineers who study these ancient sites often express a sense of awe. One professor noted that we are still trying to catch up to the intuitive wisdom embedded in these stones. They were not fighting nature's power, they were collaborating with it. This paradox forces us to look closer, to question our assumptions about strength and flexibility, and to uncover the lost principles that gave these monuments their eternal grace. The master stonemasons of the ancient world approached their work like a three-dimensional puzzle. Each stone was not merely stacked, but meticulously carved to fit its neighbor with astonishing precision. This technique, known as dry stone construction, used no mortar at all. The stones were held in place purely by their own interlocking geometry and immense weight. You can see this perfection in the jigsaw-like walls of Inca sites like Machu Picchu, where even after 500 years in one of the most seismically active regions on Earth, you cannot slip a piece of paper between the stones. So how does this create such incredible earthquake resistance? The secret lies in the joints. When the ground shakes, these perfectly fitted stones are allowed to dance. They can shift, rock, and rotate minutely against one another. This movement absorbs and dissipates the earthquake's energy as friction, a process engineers call damping. The entire structure becomes a flexible, monolithic entity that moves with the tremors. It sways and settles rather than cracking apart. Now, compare this to a typical modern concrete panel building. The panels are strong, but they are rigidly bolted or welded together at specific connection points. When seismic waves hit, these connection points become stress concentrators. All the force of the earthquake focuses on these few, rigid joints, which eventually snap under the strain. It is a classic case of a chain breaking at its weakest link. The ancient builders understood something we often forget. True strength is not always about rigid, unyielding resistance. By creating a structure of countless interlocking parts, they built a system that could gracefully yield to immense forces, then simply settle back into place once the shaking stopped. They designed their buildings not as fortresses against nature, but as partners in its eternal dance. But the stones themselves were only half of the ancient secret. The true magic often lay hidden in the glue that held them together. Journey to a construction site in ancient China, where masons are not just mixing sand and water. They are stirring in sticky rice soup, creating a mortar with a surprising ingredient. In Rome, builders blended volcanic ash with lime and seawater, producing a concrete that seemed to defy the ages. These were not random recipes. They were sophisticated formulas that gave the mortar itself a kind of life. While our modern cement is designed to be rigid and unyielding, these ancient mixtures were engineered to be flexible. The organic additives like rice paste created a polymer-like network within the mortar. On a microscopic level, this network could stretch and deform slightly, absorbing energy without snapping. Think of it like the difference between a dry, brittle twig and a fresh, green branch. The twig, like modern cement, will break with the slightest bend. The green branch, like the ancient mortar, can flex and then return to its original shape. This flexibility was the perfect complement to the shifting stone blocks, allowing entire walls to sway as a single, cohesive unit. The Roman recipe was perhaps the most miraculous. Modern laboratory analysis has shown that their concrete, especially in marine environments, does not simply endure the sea. It thrives in it. Seawater percolates through the material, reacting with the volcanic ash and lime to form new, interlocking minerals. These minerals actually fill in microcracks over time, making the concrete stronger with each passing century. Our modern Portland cement, by contrast, is chemically stable. It sets hard and fast, but it has no capacity for self-healing. When stressed by constant shaking, micro-cracks form and spread relentlessly until the entire structure fails. The ancient builders created a living material that collaborated with the elements. We create a dead, brittle material that fights them. In our pursuit of speed and standardization, we chose the simplicity of rigid perfection over the resilient wisdom of controlled flexibility. We built a fortress when we should have built a dancer. This profound respect for the earth extended far beyond the walls and deep into the ground itself. Ancient builders understood that the most resilient structure is only as strong as what it stands upon. While we today often choose building sites based on urban grids and available space, ancient engineers selected locations through a lens of deep geological wisdom. They sought out solid bedrock, anchoring their temples and monuments directly to the planet's unshakable bones. In an earthquake, the entire rock formation moves as one single, colossal unit. A structure built upon it rides this massive slab like a passenger on a great ship, experiencing the wave of energy, but not the violent, tearing forces that destroy buildings on unstable ground. This was not a matter of luck. It was the result of knowledge patiently accumulated over centuries, a generational understanding of how different soils behave when the earth trembles. They learned to avoid soft, waterlogged ground that turns to liquid under stress, and instead sought the unwavering stability of solid stone. Look at the foundations of the Egyptian pyramids. They are not merely placed on the sand. They sit upon immense, perfectly leveled platforms of stone that act like a giant's foot, distributing the colossal weight of the pyramid evenly across a vast area. This prevents what engineers call differential settlement, where one part of a structure sinks more than another, creating catastrophic twists and cracks. The pyramid's foundation ensures the entire monument settles as one, a unified mass resisting the ages. Now consider the modern city. We build on filled land, former swamps, and artificially leveled hills, all in the name of valuable real estate. Our foundations are engineered to compensate for these poor conditions, but they are fighting an uphill battle against the inherent instability we chose to ignore. The ancient approach reveals a fundamental divergence in philosophy. They worked in partnership with the earth's raw power, choosing their ground with reverence. We have sacrificed that deep geological foresight for the efficiency of development, building where we want instead of where we should. Yet this ancient mastery of the Earth was matched by a profound understanding of the skyward forces they were building against. The Great Pyramids and Gothic cathedrals stand as monuments to a forgotten principle of construction, one that harnessed immense weight as a source of strength. Ancient builders were the original masters of gravity architecture, designing structures where every stone's load flowed along deliberate, calculated paths down into the earth. They understood that mass, when properly directed, could create an unshakable equilibrium. Think of a pyramid's majestic form. Its stepped triangular sides are not merely an aesthetic choice. They are a perfect engineering diagram, channeling the colossal weight of millions of stones downward and outward in a stable, ever-widening base. This design creates a low center of gravity and a wide footprint, making it incredibly difficult to topple. During an earthquake, this sheer mass provides immense inertial resistance. The building is so heavy that the seismic waves struggle to set it into violent motion. It prefers to remain at rest, absorbing the energy through its own colossal weight. This principle is brilliantly displayed in the Gothic cathedrals of Europe. Their soaring stone vaults created tremendous outward thrust, a force that could easily push the walls apart. The solution was not to make the walls thicker, but to redirect this force. Flying buttresses act like stone ribs, gracefully catching the thrust from the roof and channeling it down into the ground at a distance. The entire structure becomes a dynamic web of balanced forces, where weight is not a burden to be overcome, but a stabilizing energy to be managed. The Mayans employed a similar wisdom in their stepped pyramids, where each ascending tier is smaller than the last, ensuring a stable, triangular load distribution that resists overturning. Now compare this to many modern skyscrapers and apartment blocks. In our quest for efficiency and height, we have embraced lightweight construction. Steel frames and glass curtain walls are engineered to be as light as possible. While this allows for incredible heights, it creates a dangerous susceptibility during seismic events. A lighter building is far easier for an earthquake to set into violent, whiplashing oscillations. Without the damping effect of immense mass, these structures can sway dangerously, causing the contents to shake apart even if the frame remains standing. The ancient approach reveals a fundamental philosophical split. We see weight as an enemy to be minimized, a cost to be reduced. They saw weight as an ally to be mastered, a source of stability to be strategically deployed. They built with the wisdom of the mountain, understanding that a massive, grounded form can withstand storms that would scatter a field of feathers. This intricate dance of stone and earth reveals an even deeper layer of genius. Ancient builders wove natural damping systems directly into their creations. They understood that to survive a quake, a building must not fight the energy, but must have a way to safely shed it. Think of the slight, intentional gaps between perfectly fitted stones in an Inca wall. These are not flaws. They are microscopic expansion joints, allowing each block to grind and shift against its neighbor. This friction converts the violent, shaking energy of the earthquake into harmless heat and sound, dissipating it gradually across millions of tiny contact points. The entire wall becomes a passive damping system, absorbing the shock like a car's suspension smoothing out a bumpy road. This principle of controlled flexibility reaches its most elegant form in the soaring wooden pagodas of Japan. For centuries, these multi-tiered towers have withstood some of the most powerful tremors on the planet. Their secret lies in a central pillar, a massive tree trunk that runs up through the center of the structure. But this pillar is not firmly anchored at its base. It is suspended, almost like a giant pendulum, hanging loosely from the complex wooden frame of the upper stories. When an earthquake strikes, the outer layers of the pagoda sway in one direction, while this heavy central column swings independently in the opposite rhythm. The two masses counterbalance each other, dramatically reducing the overall sway and preventing the building from whipping itself to pieces. It is a breathtakingly simple and effective shock absorber, conceived centuries before the term was ever coined. Similarly, the intricate wooden brackets of traditional Chinese halls, known as dugong, are a masterpiece of distributed movement. These interlocking wooden arms form a complex cloud of joints beneath the heavy tiled roofs. There is no single nail or rigid fastener. Instead, each joint is designed to flex and compress minutely. When seismic waves hit, the energy is not concentrated at a few critical points. It is shared and dissipated across hundreds of these small, flexible connections. The entire roof structure breathes and shifts as a single, organic entity, allowing for multiple small movements that prevent a single, catastrophic failure. Modern structural engineers are only now fully appreciating the sophistication of these ancient systems. Our most advanced earthquake-resistant buildings use base isolators, which are essentially giant rubber and lead bearings that separate the building from its foundation, allowing it to slide during a quake. We install massive tuned mass dampers at the tops of skyscrapers, heavy weights that swing to counteract the building's sway. These are brilliant, high-tech solutions, but they are expensive, complex additions to a rigid design. The ancient builders achieved a similar, and in some ways superior, result through the very essence of their construction. Their damping was not an added component. It was an inherent quality of the structure itself, born from generations of observing how wood, stone, and earth behave under stress. They did not need to add shock absorbers because they built the entire structure to be one. Deep within the quarries, a master mason would spend years, sometimes his entire life, getting to know the stone. He was not just cutting blocks, he was reading them, searching for the perfect piece of stone for the perfect place in the structure. His tools were his hands, his eyes, and a hammer that sang a different note when it struck a stone with the right internal qualities. This ancient art of selection was the first and most critical line of defense against earthquakes. The mason was looking for more than just a strong rock. He was seeking a specific crystalline structure and grain orientation. A stone that might shatter under a direct blow could be perfect for a section of wall that needed to flex and sway, its internal lattice of microscopic fractures acting like a built-in shock absorber. Think of it like the difference between a solid pane of glass and a car's safety glass. The solid pane, like a homogeneous stone, cracks in one clean, catastrophic break. The safety glass, with its internal network of micro-fractures, crumbles but holds together, dissipating the energy across countless tiny fault lines. Ancient builders intuitively understood this principle of controlled failure. They would carefully match stone types to structural functions. Softer, more flexible stones were chosen for infill and wall sections, where their ability to deform slightly could absorb tremors. Immense, dense stones with interlocking crystal structures were reserved for cornerstones and load-bearing columns, where unyielding strength was paramount. Modern laboratory analysis has confirmed this wisdom. Geologists studying stones from ancient temples have found that the natural variations and micro-cracks within them do not represent weakness. Instead, they create a complex internal landscape that scatters and dampens seismic waves, preventing a single, destructive shock wave from traveling cleanly through the material. Now, hold this idea in your mind and compare it to modern concrete. Our primary building material is engineered for uniformity. Every batch is mixed to be chemically and physically identical, a homogeneous soup that sets into a monolithic slab. This predictability is excellent for speed and cost, but it is a disaster for earthquake resistance. When a seismic wave hits a uniform concrete wall, it meets no internal resistance, no variations to break its path. The energy transmits through the material with terrifying efficiency, seeking out the weakest point, usually a rigid joint or a steel rebar, and unleashing its destructive force there. The ancient builder did not see a stone's unique internal character as a flaw to be eliminated. He saw it as a hidden strength to be strategically deployed. He worked in harmony with nature's infinite variations. We, in our quest for control and efficiency, manufacture a brittle uniformity that fights nature's chaotic power at every turn. We created a perfect, predictable material that fails in a perfectly predictable way, while they harnessed an imperfect, variable material that succeeded in unpredictably brilliant ways. This lost wisdom of selective, intentional building leads us directly to the single most critical flaw in our modern approach to construction, a flaw that lies not in our materials but in our very mindset. This obsession with perfect proportion was etched into the very blueprints of survival. When an ancient Greek architect laid out the foundation for a temple, he did not rely on arbitrary measurements. He used a sacred ratio, a mathematical relationship found in seashells and sunflowers, known today as the golden ratio. This proportion, roughly 1.618 to 1, creates a rectangle that the human eye finds inherently pleasing. But its purpose was far more than aesthetic. Modern engineering analysis reveals that structures built with these specific proportions have a unique dynamic stability. Their geometry naturally channels vibrational energy in ways that prevent the buildup of destructive resonance. A Greek temple is not a solid block. It is a forest of columns, and when an earthquake's waves pass through, the specific spacing and height dictated by the golden ratio cause the entire structure to vibrate at frequencies that differ from the dominant, ground-shaking pulses of most quakes. The building essentially sings a different song than the earthquake, avoiding the catastrophic harmony that would shake it apart. This is harmonic resistance, a principle we now achieve with supercomputers, but which they encoded through intuitive geometry. The form itself was a shock absorber. The same wisdom shaped the magnificent dome of the Roman Pantheon. A perfect hemisphere of concrete, it stands as the world's largest unreinforced concrete dome, enduring for nearly 2,000 years. The circle is nature's most efficient shape for distributing force. Unlike a square building with vulnerable corners where stress concentrates, the Pantheon's circular base and domed roof have no weak points. When seismic energy arrives, it travels smoothly around the continuous curve, spreading the force evenly across the entire structure. The stress does not get trapped or focused. It flows like water around a stone, leaving the building intact. This is why so many ancient tombs, granaries, and temples were round. It was a deliberate choice for stability, creating a form that had no obvious direction to fail. Stepped pyramids in Mesoamerica and Egypt employ a different kind of geometric genius. Their tiered, receding levels are not just a staircase to the heavens. They are a masterpiece of redundant load paths. Imagine pouring a bucket of water over a stepped pyramid. The water would cascade down from one level to the next, its energy dissipated at each ledge. Now imagine that water is the force of an earthquake. Each step acts as a separate, stable platform, breaking the upward flow of seismic energy. If one stone on a lower level shifts, the level above remains largely unaffected, its weight distributed across the wide platform beneath it. The stress is forced to find a new, longer path to travel, and with each detour, its destructive power fades. This creates a structure with immense redundancy, where the failure of a single element does not lead to a total collapse. Modern engineering is only now fully appreciating the power of these forms. We build rectangular boxes because they are easy to design and furnish, but their 90-degree angles are natural amplifiers for seismic stress. The ancient builders, through their sacred geometry, were not just constructing monuments, they were composing a silent symphony of stability, using the universal language of mathematics to create forms that could argue with the earth itself and survive the debate. This slow, generational transfer of knowledge was the lifeblood of architectural resilience. The master mason did not work from a static blueprint tucked in a tube. He carried a living library of techniques in his hands and his heart, a library meticulously copied from his own master and refined through a lifetime of practice. This was the guild system, a centuries-long chain of human connection where wisdom was passed not in lectures, but through shared labor. An apprentice would spend his first years merely mixing mortar, learning its texture and behavior in different weather. He would graduate to roughing out stones, and only after decades might he be trusted to carve a critical cornerstone. This was not just job training, it was the embodiment of cumulative intelligence. Every technique, every subtle nuance in how to fit a joint or select a stone had been tested and proven by generations before him. The knowledge was dynamic, constantly being updated. If a tremor caused a new crack in a temple wall that was 50 years into its construction, the current generation of masons would see it, analyze it, and adapt their technique for the next section. The building itself was a living textbook, its scars providing the most valuable lessons on Earth. A project that spanned a century was not a delay. It was a multi-generational research and development program funded by faith and built in stone. This created a profound feedback loop. The builders could observe how their structures withstood real seismic events over decades, making incremental improvements that were then encoded into the oral tradition of the craft. The slow pace was not inefficiency, it was the essential ingredient for perfecting survival. Now hold that thought and look at a modern construction site. A skyscraper rises in a matter of months. The design team creates the plans, a different contracting firm wins the bid, and a crew of workers who may never have met before assembles for this single project. They follow the standardized plans with precision, but they bring no deep, inherited wisdom about the specific land they are building upon. When the project is done, the team disbands. There is no living tradition to carry forward the subtle lessons learned, because the next project will have a different design, a different location, and a different crew. We have traded the deep, localized, generational knowledge of the guild for the universal, disposable efficiency of the project team. We have compressed centuries of learning into a 2-year construction schedule, and in that compression, we have lost the patient, observational genius that allowed ancient builders to collaborate so intimately with the unpredictable earth. Their resilience was not just in the stones they laid, but in the unbroken chain of hands that laid them, a chain that transmitted not only skill, but a reverence for the forces they were striving to withstand. Rising from the heart of Istanbul, the Hagia Sophia has defied earthquakes for 15 centuries. This magnificent structure has endured dozens of major quakes, its great dome witnessing the collapse of countless newer buildings around it. Modern additions and repairs to the cathedral have required steel braces and concrete supports, yet the original core, built by the Romans in the 6th century, stands unshaken. Its secret is a revolutionary design that masters the art of controlled movement. The dome does not simply rest on solid walls. It is cradled by 4 immense curved triangles of masonry known as pendentives. These pendentives perform a kind of architectural magic, gracefully transitioning the circular base of the dome down to a square supporting structure below. This creates a system of arches and semi-domes that channel the building's immense weight not just downward but outward. the entire structure exists in a state of perfect balanced tension, like a woven basket holding a heavy stone. When the ground shakes, this complex web of arches and curves allows the building to flex. The pendentives and arches can minutely compress and shift, absorbing the seismic energy and redistributing the forces throughout the entire shell. It is a symphony of stone where every element works in concert to prevent any single point from bearing a catastrophic load. Modern engineering studies have uncovered another layer of its genius. Seismologists have analyzed the building's natural vibrational frequency, the rate at which it naturally wants to sway. They found that the specific geometry and mass of the Hagia Sophia cause it to vibrate at a frequency that is out of sync with the dominant, ground-shaking pulses common to the region. The building essentially avoids the most dangerous seismic rhythms, swaying to its own, safer tune. This was not a lucky accident. It was the result of Roman engineering brilliance fused with a profound, localized understanding of the land's tremors. The Hagia Sophia is not merely a building that resists earthquakes. It is a building that has learned to dance with them, a perfect synthesis of mathematical ambition and earthly wisdom that continues to quietly challenge our modern assumptions of what it means to build for the future. The 5-story pagoda at Horyuji Temple has weathered over 1,400 years of Japan's violent tremors, its graceful silhouette a testament to a forgotten engineering art. These wooden towers do not resist earthquakes, they absorb them, moving with a fluid grace that rigid modern buildings cannot match. The secret is in the joints. Every beam and bracket is connected using complex woodworking joints that fit together with astonishing precision, yet without a single nail or metal fastener in the primary structure. This intricate joinery, known as nuki and watariego, creates a flexible skeleton. When the ground shakes, these wooden joints compress, stretch, and rotate, allowing the entire pagoda to sway and shudder like a tall, deeply rooted tree in a storm. The energy of the quake is dissipated as friction within this complex web of wood, preventing it from concentrating and tearing the building apart. It is a design that embraces movement as a form of survival. At the heart of this flexible shell lies its most brilliant secret, the shinbashira, or central pillar. This massive, single tree trunk runs vertically through the center of the pagoda, but it is not anchored to the ground. Instead, it hangs suspended from the upper stories, dangling just above the foundation stone. This transforms the entire central column into a giant, passive pendulum. During an earthquake, as the outer frame of the pagoda sways in one direction, the heavy shinbashira swings independently in the opposite rhythm. The two masses actively counterbalance each other, canceling out the violent whiplash that would destroy a rigid structure. You can see this principle in action during seismic tests on scale models, where the pagoda sways gently as a solid block building next to it shakes itself to pieces. The layered roofs add another layer of sophisticated damping. Each story, with its own heavy, tiled roof, is constructed as a relatively independent box, stacked loosely on the one below. These stacked masses do not move in perfect unison. Their slight, out-of-sync rocking creates internal friction that further bleeds away the earthquake's energy, much like a stack of books will shift and settle individually if you shake the table they rest on. This combination of a flexible frame, a suspended pendulum, and multiple damping masses represents a pinnacle of ancient seismic design. Modern engineers use expensive tuned mass dampers in skyscrapers to achieve a similar effect, but the Japanese carpenters built this shock-absorbing quality directly into the soul of the structure, using wood's natural resilience in a perfect collaboration with the Earth's restless power. A structural engineer who has studied both ancient temples and modern skyscrapers described the feeling as a kind of professional humility. He said, We can model a building's response to a theoretical earthquake with astonishing precision, down to the millimeter, using supercomputers. Yet we watch a 2,000-year-old temple stand through a real quake that shatters our predictions, and we have to ask ourselves, what are we missing? Modern engineering has gained an incredible depth of scientific understanding. We know exactly how forces travel through a steel beam, and we can design a skyscraper to sway safely within calculated limits. This computational precision allows us to build taller, lighter, and more complex structures than ever before. But the engineer admitted that this very precision has come at a cost. We have traded the holistic, adaptive wisdom of the ancient mason for the specialized, fragmented knowledge of the modern project team. The mason understood his site, his materials, and the local seismic personality as one interconnected system. We break that system into separate silos: geology, material science, structural engineering, and architecture, and we lose the deep, intuitive synthesis that made the ancient structures so resilient. Our building codes are a perfect example of this trade-off. These codes are scientifically rigorous, born from decades of painstaking research and tragic failures. They tell us the minimum required strength for a steel connection or the exact amount of rebar needed in a concrete column. They are designed to prevent catastrophic collapse and save lives, a goal in which they have been largely successful. But this code-based approach creates a rigid, one-size-fits-all system. A building in California and a building in Turkey might follow different codes, but both are applying standardized rules, not the site-specific intuition of a master builder who knew that one side of a valley shook differently from the other. The codes ensure a baseline of safety, but they do not encourage the kind of graceful, redundant, and adaptable design that allows a structure to survive for 1,000 years. They create buildings that are strong enough to not fall down, but not resilient enough to remain perfectly functional after the shaking stops. This leads directly to the core vulnerability of modern construction. We prioritize speed, cost efficiency, and the use of standardized, predictable materials. A construction project is a financial equation, and time is the most expensive variable. We cannot spend a decade selecting individual stones or mixing a mortar that needs years to cure. We use concrete that sets in hours and steel beams that arrive prefabricated from a mill thousands of miles away. This system allows us to house millions and build great cities with incredible speed, but it strips away the very qualities that gave ancient buildings their seismic grace. Standardized materials lack the internal variations that naturally dampen vibrations. Rapid construction eliminates the generational feedback loop that allowed ancient builders to learn and adapt. And the relentless drive for cost efficiency removes the expensive redundancies, the extra mass, and the intricate, flexible joints that are not strictly necessary to prevent collapse, but are absolutely essential for long-term resilience. The trade-off becomes starkly clear when you consider modern functionality. We demand large, open floor plans without supporting columns, complex networks of electrical and plumbing utilities running through our walls, and vast windows offering panoramic views. These features are wonderful for living and working, but they are a seismic engineer's nightmare. A large, open space lacks the internal walls that would otherwise act as shear walls, bracing the structure against sideways movement. The utilities, when rigidly attached to the building's frame, can be shattered by even minor flexing, cutting off water and power precisely when they are most needed. Our modern buildings are complex machines, and their very complexity introduces thousands of potential points of failure that simply did not exist in a solid stone pyramid or a flexible wooden pagoda. So what have we truly gained and lost? We have gained the ability to build on an unprecedented scale and with incredible speed, sheltering populations and creating cities of breathtaking verticality. We have gained the power of prediction, using science to model and mitigate disaster, but we have lost the patience for deep collaboration with a specific place. We have lost the holistic view that saw a building not as a collection of separate components, but as a single, living system in dialogue with the Earth. We built a world of miraculous efficiency, but in the process we may have forgotten how to build for the millennia. This fundamental difference in philosophy is written in the very stone and concrete we build with. Inside a geology laboratory, a core sample of ancient granite tells a story of resilience. Under a powerful microscope, it reveals a complex, chaotic mosaic of interlocking crystals, each with a different size, shape, and orientation. This heterogeneous composition is its secret strength. When a seismic shock wave enters this material, it does not travel in a straight line. It is forced to zigzag and scatter, bouncing off countless crystal boundaries and internal imperfections. Each of these tiny deflections saps a minuscule amount of the wave's energy, converting it into harmless heat. The journey through the stone is a turbulent, exhausting one for the destructive force, which arrives on the other side significantly weakened. It is a material with built-in multi-path energy dissipation. Now place a sample of modern concrete under that same microscope. The view is startlingly uniform. It is a homogeneous matrix where the aggregate is suspended in a consistent cement paste. This engineered uniformity, so prized for its predictable strength, becomes a fatal flaw under dynamic stress. A seismic wave passes through this uniform material with terrifying efficiency. It meets no internal resistance, no chaotic landscape to break its momentum. The energy transmits cleanly and powerfully through the slab, seeking out the weakest point, often the rigid bond with the steel rebar, and unleashing its full, concentrated force there. This is why concrete fails so catastrophically. It does not bend or absorb, it waits and then it shatters. The contrast becomes even more dramatic when we examine how these materials fail. The crystalline structure of granite or limestone allows for what material scientists call microfracturing. Under immense pressure, tiny, internal cracks form and spread along the natural boundaries between crystals. This process absorbs a massive amount of energy, like a car's crumple zone deforming to protect the passengers. The stone sacrifices tiny, internal flaws to save the whole structure from a single, clean break. Concrete, however, lacks this graceful failure mode. Its internal structure is brittle. Once the stress exceeds its tensile strength, a single, dominant crack forms and propagates rapidly through the uniform material, resulting in a sudden, complete, and catastrophic failure. The laboratory footage is unequivocal. A sample of ancient lime and ash mortar is subjected to increasing pressure. It visibly flexes and deforms, developing a web of fine, hairline cracks that slowly spread, but the sample holds together, continuing to bear the load. It behaves like tough, fibrous leather. Then, a sample of modern Portland cement is tested. It remains rigid and unyielding until, at a specific stress point, it explodes into fragments with a loud crack. It behaves like a piece of chalk. This is the material science reality that ancient builders understood through generations of trial and observation. They did not need a microscope to see that a stone with varied coloration and texture performed better in a tremor than a perfectly uniform one. They selected for heterogeneity, for a built-in ability to bleed off energy through countless internal battles. We, in our quest for control, manufacture a material that is strong in a steady state but brittle under the chaotic, dynamic loads of an earthquake. We built with a substance that fights the shock wave head-on, while they built with materials that invited the wave in and gracefully exhausted it. A crack appearing in a temple wall was not seen as a failure, but as a conversation. For ancient societies, the work of building was never truly finished. It was a sacred covenant with the future, a cycle of care passed from one generation to the next. When an earthquake shook loose a few stones or cracked the mortar, it was not a disaster demanding a rushed, identical repair. It was an opportunity. The masons who arrived to fix the damage were often the descendants of the original builders, inheriting both the tools and the responsibility. They would study the failure, learning exactly how the forces had moved through the structure. Then they would not merely replace the stone, they would recarve the joint for a tighter fit, or they might subtly alter the mortar recipe based on what they had observed, creating a slightly more flexible bond in that specific, vulnerable location. This continuous, mindful repair was a form of evolutionary refinement. Over centuries, a structure was not just maintained, it was actively upgraded. Its weaknesses were systematically identified and corrected, its seismic performance honed with every tremor it survived. The repointing of mortar joints was a particularly vital ritual. As old mortar crumbled, it was carefully chiseled out and replaced with fresh, often improved mix. This process did more than just fill a gap. It reintroduced flexible, living material into the building's skin, restoring its ability to sway and absorb energy. Each repair was like healing a small wound with stronger tissue, leaving the structure more resilient than it was before the quake. This stands in stark contrast to our modern relationship with buildings. We construct them with the expectation that they will remain static, their maintenance often an afterthought deferred until a leak appears or a facade becomes dangerous. We treat our buildings like disposable appliances, running them until a critical component fails, then embarking on expensive, disruptive repairs that aim only to restore the original, flawed condition. We patch the symptom without ever addressing the underlying vulnerability. The ancient approach to stewardship created a living structure that adapted and improved over time, learning from its battles with the earth. Our modern buildings, however, almost always deteriorate from their original design condition. Their joints weaken, their materials fatigue, and their hidden vulnerabilities remain unaddressed until a major seismic event reveals them all at once with catastrophic consequences. This cultural shift represents a lost dimension of resilience. It is the difference between caring for a centuries-old tree, patiently pruning and supporting its growth, and assembling a plastic model that is perfect on day one but can only ever decay. One system embraces time as a partner in strengthening, while the other fights a losing battle against it. These ancient builders possessed a genius for turning everyday challenges into hidden strengths. A structure's struggle against the desert sun or the monsoon rain was not separate from its fight against earthquakes. It was part of the very same battle for survival. In the arid heartlands of the Middle East, architects faced a relentless enemy, the scorching heat. Their solution was to build with immense thermal mass, using incredibly thick walls of mud brick or stone. These walls acted like a thermal battery, absorbing the sun's heat during the day and slowly releasing it through the cool night, creating a stable indoor climate. But this adaptation for comfort created a powerful seismic side effect. All that mass, distributed evenly through thick, heavy walls, gave the building tremendous inertia. During an earthquake, the ground might lurch violently, but a building with such profound weight and a low center of gravity resists being thrown into destructive motion. It prefers to stay at rest, its bulk absorbing and dampening the energy that would shatter a lighter, thinner structure. The desert home, designed to tame the sun, was unknowingly engineered to stand firm against the shaking earth. Meanwhile, in the rainy highlands and tropical climates, the primary threat was water. Here, builders designed steeply pitched roofs, not merely for aesthetics, but to shed torrential downpours quickly, preventing the accumulation of weight that could collapse a flatter roof. To manage the runoff, they constructed elaborate systems of gutters, downspouts, and drainage channels that directed water away from the foundation. This careful attention to water management created a perfectly balanced structure. The steep roof prevented uneven, heavy loads of water or snow from accumulating on one side. The effective drainage kept the soil around the foundation stable, preventing erosion and liquefaction during a quake. The entire building became a lesson in equilibrium, its weight distributed in a way that resisted the twisting, off-balance forces an earthquake creates. In coastal and mountainous regions constantly battered by wind, builders intuitively crafted aerodynamic forms. They rounded the corners of towers, streamlined the profiles of pagodas, and designed gently sloping roofs that allowed powerful gusts to flow around the structure with minimal resistance. This shaping for wind had a profound seismic benefit. Earthquakes do not just push up and down, they generate powerful horizontal forces that slam into a building's face. A sharp-cornered, flat-walled modern building presents a solid, unforgiving surface to these forces, which hit like a hammer. But an ancient, rounded tower or a pagoda with its gracefully curved eaves presents a slippery, faceted surface. The horizontal energy does not strike a single flat plane. It is deflected, broken apart, and guided around the form, much like wind flowing over a wing. The shape that helped the building survive a hurricane also helped it survive an earthquake by dissipating those lateral shocks. This is the core of the ancient advantage, a holistic resilience. They were not solving for one variable at a time. They were crafting integrated solutions that addressed heat, water, wind, and the unseen threat of seismic activity all at once. Their buildings were multi-tooled survivors, honed by their environment to withstand a multitude of assaults. Modern engineering, by contrast, often operates in silos. We install separate HVAC systems for climate control, independent drainage for water, and distinct structural reinforcements for seismic loads. This specialization allows for incredible optimization in each area, but it can create a fragile house of cards where each system depends on the others not to fail. The ancient builders' approach was inherently redundant and robust because every feature served multiple, intertwined purposes. The thick wall was both an air conditioner and a seismic damper. The steep roof was both a water shedder and a stability aid. They built for the whole of their world, and in doing so, they created structures that could endure its every mood. That generational perspective was the most powerful tool in the ancient builder's workshop, a tool we have completely lost. We live in an era of quarterly profits and election cycles, but ancient societies operated on a timeline measured in lifetimes. A master mason would lay the foundation for a cathedral knowing he would never see it spire. His son would continue the work, and his grandson would place the final stone. This was not a failure of planning, it was the very engine of their success. A project spanning a century became a living laboratory. If an earthquake struck when the walls were only halfway up, the builders could study the precise pattern of cracks, understand how the forces had traveled through their nascent structure, and adapt their technique for the next phase. The building itself taught them, and the slow pace gave them the time to listen and learn. Every tremor was a lesson, every crack a teacher. This created a cumulative intelligence, a feedback loop of resilience that was literally set in stone. The spiritual dimension of their work elevated it far beyond mere construction. A temple was not a piece of real estate, it was a bridge to the divine, a permanent home for the gods. This sacred purpose justified any amount of time and any expense. The motivation was not profit, but honor, legacy, and cosmic order. A builder cutting a cornerstone was not just shaping a rock, he was participating in a ritual that would outlive his civilization. This mindset fostered an uncompromising standard of quality. There was no client demanding a faster completion date to save money, no shareholder expecting a return on investment. The only deadline was eternity. This freedom from economic pressure allowed for a kind of perfectionism that is unthinkable today. Stones could be rejected for invisible flaws, mortar could be left to cure for years, and designs could be refined over decades. The ancient builders' relationship with time was one of collaboration, not conquest. They saw themselves as one link in a great chain, receiving wisdom from the past and adding to it for the future. We, however, see time as an enemy to be beaten. Our construction schedules are battles against the clock, where speed is victory and delay is defeat. We have sacrificed the profound, patient wisdom of the multi-generational project for the relentless efficiency of the 2-year build. We gained incredible speed, but we lost the deep, observational learning that transforms a mere building into a living, breathing partner with the earth itself. The silent ruins of ancient cities hold more than just history. They contain a detailed forensic report on survival. Archaeologists walking through the rubble of a site shattered by an ancient quake do not see chaos. They read a story written in stone, where every fallen column and fractured wall speaks volumes about what succeeded and what failed. A temple's inner sanctum remains perfectly intact while its grand entrance colonnade lies in a heap of drums. This pattern is not random, it is a direct testimony to the strength of a compact, well-supported core versus the vulnerability of a long, open portico. The way stones have fallen provides a vector map of the seismic forces, revealing which walls acted as shear panels, bracing the structure, and which were merely decorative partitions that offered no resistance. A single, still-standing arch amidst a field of debris is not a miracle. It is proof of concept, demonstrating the superior load distribution of a curved form over the right-angled corners that crumbled around it. The evidence is literally set in stone. Look at the cracks themselves. A jagged, lightning bolt fracture running through a foundation slab tells of a sudden, brittle failure. But a series of fine, hairline cracks stepping up through a mortar joint reveal a different story, one of gradual, ductile yielding that absorbed energy and saved the wall from a catastrophic split. Archaeologists can even distinguish between repairs made after different seismic events. A section of wall with stones of a slightly different color or tooling pattern indicates a repair, a patch applied by ancient masons who learned from a previous quake's damage. The original mortar might be hard and crystalline, while the repair mortar is more flexible, mixed with organic additives discovered through trial and error. Each repair layer is a page in a centuries-long logbook of seismic adaptation. The most telling evidence comes from comparative analysis. Why did one Roman villa in Pompeii collapse into dust while its neighbor, built with the same materials and techniques, suffered only minor damage? The answer is often found in the subtlest of details. The surviving villa might have slightly thicker walls at a critical junction, or its foundation might have been dug just a few feet deeper, anchoring it to a more stable layer of soil. It might feature a different pattern of wooden beam inclusions within the stonework, creating a flexible lattice that the collapsed building lacked. These are not grand architectural innovations. They are the small, critical refinements that separated survival from total failure. This empirical evidence, gathered from countless ruins across the world's fault lines, forms a vast, unspoken database of seismic design. It is the physical result of the ancient trial and error process, where failures were not hidden but studied, and successes were meticulously replicated and improved upon for generations. The ruins are not just monuments to the past, they are the most honest and enduring textbooks on resilience ever written. The ruins are no longer just relics for archaeologists to study. They are becoming blueprints for a new generation of architects and engineers. In a quiet laboratory, a team is testing a set of interlocking concrete blocks, their design lifted directly from the jigsaw walls of Machu Picchu. These are not simple cubes. Each block has a complex, three-dimensional geometry that fits with its neighbors like a key in a lock. When assembled into a wall without mortar, they create a structure that can sway and shift during an earthquake, then settle back into perfect alignment. This is not a theoretical exercise. Projects are already underway to use these interlocking blocks for retaining walls in seismic zones, and even for the cores of low-rise buildings, creating modern structures with the same inherent flexibility as an ancient Inca fortress. High above the city, in the skeleton of a new skyscraper, another ancient secret is being reborn. Engineers are installing flexible joint systems inspired by the intricate wooden brackets of Japanese pagodas. Instead of rigidly welding steel beams together, they are designing connections that allow for a controlled amount of rotation and movement. These joints act like the dugong of a traditional Chinese hall, distributing seismic energy across hundreds of small, yielding points instead of concentrating it at a few vulnerable spots. One structural engineer who has spent years studying historical structures explained his philosophy. He said his goal is not to fight every force with brute strength, but to design a building that knows how to dance. He described watching slow-motion video of a pagoda in an earthquake, its layers moving in a fluid, almost wave-like motion, and he realized that our modern buildings are too stiff, too rigid in their resistance. His latest design incorporates a central concrete core that is deliberately designed to flex and absorb energy, a direct homage to the suspended pillar in a Japanese pagoda. Perhaps the most exciting frontier lies in the very stuff that holds our buildings together. Material scientists are now looking at ancient Roman recipes not as historical curiosities, but as formulas for the future. They are developing new composite materials that mimic the behavior of sticky rice mortar and self-healing Roman concrete. One team has created a polymer fiber reinforced concrete that contains tiny, encapsulated healing agents. When a microcrack forms, the capsules rupture and release a gel that hardens, effectively stitching the crack closed, just as Roman concrete grew stronger over time through chemical reactions. Another group is experimenting with a flexible biopolymer additive derived from plant starches, creating a cement that can bend slightly without fracturing. This research moves us away from the brittle perfection of modern Portland cement and toward a living, adaptable material that collaborates with stress instead of succumbing to it. This is not a rejection of modern engineering, but a vital synthesis. We are finally learning to merge our computational power with the intuitive, holistic wisdom of the past. We can use supercomputers to model the exact stresses on a building inspired by the golden ratio, or to optimize the placement of modern flying buttresses that channel force away from a glass tower. The architect who studies the Hagia Sophia is not trying to replicate its dome in concrete. She is seeking to understand the principle of balanced tension, of how to create a building that exists as a unified system of forces. This fusion represents our best hope for creating a truly resilient future, one where our buildings are not just strong enough to avoid collapse, but are graceful enough to remain standing, fully functional for centuries to come. The ancient builders left us a legacy written in stone, and we are finally beginning to read it not as a history lesson, but as a guidebook for our survival. This financial perspective shatters our modern definition of value. let us conduct a radical cost-benefit analysis, not over a decade, but across 1,000 years. The initial price tag for a Roman temple was undoubtedly immense, consuming a significant portion of an empire's wealth. But that structure is still standing today, having required only periodic, minor maintenance over 2 millennia. Now calculate the true cost of a modern commercial building with a 50-year design life. You must add the original construction cost, then the multi-million-dollar bill for seismic retrofitting after 30 years, and finally the colossal expense of its complete demolition and replacement after it becomes obsolete or damaged beyond repair. Repeat this cycle of build, repair, and rebuild every half-century for 2,000 years. Suddenly, the ancient temple's staggering initial investment looks like the most frugal long-term deal in human history. The ancient perspective was fundamentally intergenerational. A pharaoh commissioning a pyramid understood he was spending his kingdom's treasure not for his own reign, but for an eternal legacy. The economic model was one of a single, monumental capital expenditure intended to last forever. Our modern economic model, driven by quarterly reports and short-term loans, is built on planned obsolescence and rapid depreciation. We prioritize the lowest upfront cost to maximize immediate profit, a decision that creates a relentless cascade of future expenses we conveniently leave for our grandchildren to solve. This divergence stems from a deep cultural split in how we view permanence. Ancient societies saw their greatest buildings as eternal statements of cultural identity, anchors for civilization itself. Disposability was a concept reserved for tools, not temples. We, however, live in an age of accelerating change, where buildings are often treated as financial assets to be leveraged, depreciated, and then discarded when a newer, more profitable model can be erected. We build for the present market, not for the distant future. This economic reality forces a brutal compromise. The intricate, flexible joinery of a Japanese pagoda is too labor-intensive for a modern budget. The century-long curing process of perfect Roman concrete is incompatible with a 2-year construction loan. The meticulous selection of individual stones by a master mason is impossibly expensive when compared to the standardized factory-produced concrete panel. In our quest for affordability and speed, we systematically engineered out the very features that grant long-term resilience. The final calculation is sobering. When you measure true cost not in currency, but in continuous resource consumption, energy expended on constant rebuilding, and the environmental toll of endless construction waste, our modern, efficient approach is revealed as profoundly wasteful. The ancient builders made a massive, one-time investment in the Earth's mineral wealth and created an asset for millennia. We make smaller, repeated withdrawals from the same planetary bank account, forever paying interest on a debt of durability we chose not to settle. Their philosophy was one of ultimate sustainability, building once and building right. Ours is a cycle of consumption that mistakes a low initial price for genuine economic wisdom. A temple was never just a building. It was a living map of the cosmos, a physical anchor connecting the human realm to the divine. This profound spiritual purpose demanded more than mere structural integrity. It required a deep, harmonic resonance with the natural world. The architects were not just engineers, they were philosophers and priests, translating sacred geometry and celestial patterns into stone. The perfect proportions of a Greek temple, for instance, were not an aesthetic whim. They were a deliberate echo of the mathematical order believed to govern the universe, a harmony that, by its very nature, created a form inherently resistant to chaotic forces like earthquakes. To build a microcosm was to build something in perfect balance, and a structure in balance is incredibly difficult to topple. This cosmological vision dictated every aspect of construction. A pyramid was not a tomb, it was a ramp for the pharaoh's soul to ascend to the stars, and its immense, stable form had to withstand the ages to fulfill that eternal duty. In Hindu temple architecture, the entire structure is a representation of the cosmic mountain, Mount Meru, with its towering, tiered spire designed to draw energy upward and channel it safely back down. The form itself was a prayer for stability, a physical manifestation of the universe's enduring order. How did this spiritual understanding translate into tangible resilience? The concept of divine balance demanded flawless execution. A single misaligned stone was not just a construction error, it was a spiritual flaw, a crack in the cosmic order that could invite disaster. This belief system enforced an almost superhuman level of quality control. Rituals accompanied every phase of construction, from the quarrying of the first stone to the placement of the final capstone. The foundation trench was not merely dug, it was consecrated. Offerings were placed beneath cornerstones, not as superstition, but as a solemn covenant with the earth, a ritualistic plea for the land to accept and support the structure. These ceremonies were not separate from the engineering. They were the psychological and cultural engine that ensured the engineering was perfect. The masons were not laborers, they were participants in a sacred act. This spiritual dimension cultivated a mindset where every joint, every carving, every batch of mortar was infused with intention and reverence. There was no room for cutting corners, because a corner cut was an insult to the gods. This holistic fusion of meaning and material created structures that were cherished as living entities. A temple was maintained, repaired, and preserved not just because it was useful, but because it was sacred. This continuous, devoted stewardship meant that weaknesses were addressed with the same care as the original construction, creating a feedback loop of preservation that spanned centuries. Modern engineering, for all its computational power, struggles to replicate this profound motivation. We build to a code, a set of minimum standards for safety. They built to a covenant, a promise of eternal harmony. We create structures that are technically sound. They created structures that were spiritually and structurally unified, and in that unity, they found a resilience that we are only now beginning to fully comprehend. Yet for all their seismic genius, these ancient builders faced constraints we have long since surpassed. Their methods were perfected for temples, tombs, and palaces, structures designed for gods and kings, not for the complex needs of millions of people living and working in dense urban centers. You could never build a 50-story hospital or a sprawling airport terminal using the interlocking stones of Machu Picchu. The sheer mass required would be astronomically heavy, and the interior spaces would be a forest of thick support columns, making large, open floors impossible. Ancient construction excelled at creating durable, monumental shells, but it was fundamentally ill-suited for the vast, flexible interiors our modern world demands. Imagine a contemporary operating room with its need for sterile environments, intricate plumbing, electrical systems, and wide, unobstructed spaces for advanced medical equipment. A stone vault, no matter how earthquake-resistant, could never accommodate the tangle of utilities and the need for reconfigurable layouts that define a modern hospital. Our buildings are not just shelters, they are complex machines for living and working, and this complexity introduces vulnerabilities that ancient builders never had to consider. We also face safety challenges they could never have imagined. Ancient structures had no requirements for fire escapes, wheelchair-accessible ramps, or emergency lighting. A stone temple could survive a quake but become a deadly trap in a fire with no safe egress paths. Modern building codes, for all their potential rigidity, are built upon a century of hard-learned lessons about fire safety, accessibility, and emergency response, creating a web of requirements that go far beyond mere seismic survival. This is not to dismiss the ancient wisdom, but to place it in a realistic context. We cannot house our global population in low-rise, massively thick stone buildings. We cannot power our cities with structures that have no cavities for electrical wiring or plumbing. The challenge, then, is not to abandon modern engineering, but to thoughtfully integrate the resilient principles of the past into the complex, large-scale necessities of the present. We must learn from the ancient dancer's grace without sacrificing the modern world's vital functions. Inside a seismic testing laboratory, two miniature buildings stand side by side on a massive shaking table. One is a scale model of a modern concrete frame building, the other a precise replica of an ancient stone structure with interlocking blocks. With the press of a button, the table begins to rumble, simulating the violent tremors of a major earthquake. The modern model immediately begins to shudder, its rigid frame amplifying the shaking until, with a sharp crack, a critical joint fails and the entire structure collapses into a heap of broken pieces. The ancient model, however, tells a completely different story. It begins to sway, its individual stones rocking and grinding against one another in a slow, graceful dance. The entire structure moves as a single, flexible unit, absorbing the violent energy and settling back into perfect alignment once the shaking stops. The only sound is the soft whisper of stone sliding against stone. This is not a theoretical comparison. It is visual, scientific proof captured in slow-motion video and precise sensor data. Engineers have covered these models with tiny sensors called accelerometers and strain gauges. These instruments paint a real-time picture of how the earthquake's destructive force travels through each building. In the modern model, the data shows sharp, jagged spikes of stress concentrating at the rigid beam-to-column connections, the energy with nowhere to go but to build until something snaps. The sensors on the ancient model reveal a smooth, rolling wave of energy that is distributed evenly across thousands of stone-to-stone contacts, its power dissipated as harmless heat through friction. The most groundbreaking tests, however, involve hybrid models. Researchers construct a modern building frame but incorporate ancient principles, using flexible joints inspired by Japanese pagodas or adding a central, suspended weight that acts like a pendulum. When subjected to the same quake, these hybrid structures perform spectacularly well, swaying gently where their purely modern neighbors would have shattered. The laboratory evidence is now undeniable. The intuitive wisdom of the ancient builders, honed over centuries of observing real earthquakes, is being validated by the most advanced scientific instruments we possess. We are finally able to see, measure, and prove the profound genius of designing a building not as an unyielding fortress, but as a partner in the Earth's eternal dance. This global tapestry of earthquake-resistant design reveals a stunning truth. Ancient builders did not follow a single universal blueprint. Instead, they developed profoundly different solutions, each perfectly tailored to the unique seismic personality and material palette of their homeland. The challenges faced by a civilization perched on the volcanic ring of fire were utterly different from those living along a continental fault line, and their architectural responses reflect this deep, localized understanding. In the Mediterranean, where powerful tremors could originate from deep within the earth, civilizations like the Greeks and Romans built with immense interlocking stone. Their seismic strategy was mass and friction, using the colossal weight of marble and granite blocks to resist being set into motion. The Parthenon's columns, with their precisely carved drums, were designed to rock and sway as a unit, their sheer bulk providing the inertia to ride out the long, rolling waves of a Mediterranean quake. Theirs was a resilience of brute force elegantly managed. On the other side of the world, in the islands of Japan, the seismic threat was more violent and shallow. Here, the earth did not roll, it snapped and jerked. The Japanese response was not to resist, but to yield with incredible grace. Their primary building material was timber, an abundant resource that offered natural flexibility. A traditional Japanese pagoda is essentially a skeletal frame of wood, designed to be light and incredibly flexible. When the sharp, jerking motions of a Pacific subduction zone quake hit, the entire structure bends and twists, its complex joinery allowing it to shudder without breaking. Where the Greeks used stone mass to dampen energy, the Japanese used wooden flexibility to absorb it. This divergence is equally stark in the Americas. High in the Andes, the Inca faced a triple threat: volcanic tremors, tectonic uplifts, and the constant risk of landslides. Their engineering solution was a masterpiece of geometric locking. The polygonal stonework of sites like Ollantaytambo or Sacsayhuaman looks like a chaotic jigsaw puzzle, but this was a deliberate defense. Each irregularly shaped stone, often hard granite or diorite, was painstakingly shaped to fit its neighbors on multiple sides. During an earthquake, these stones would shift and grind against each other, but their complex, interlocking angles prevented them from sliding too far. The wall would move, settle, and then lock back into place, its stability coming from its geometric complexity, not just its weight. This was a direct adaptation to the multi-directional shaking common in mountainous regions. The choice of material was never accidental. It was a function of what the land provided. The Egyptians had limitless sandstone and granite, so they built pyramids that were essentially artificial mountains. The Japanese had vast forests of cypress and cedar, so they crafted flexible wooden skeletons. The Romans had volcanic ash, which they mixed into a concrete that could actually heal its own cracks. Each culture looked at the raw materials beneath their feet and the tremors that shook their world, and they asked a simple, brilliant question: how can we use what we have to build something that will last? The answer was never the same twice, but the underlying principle was universal. True resilience is not a one-size-fits-all formula. It is a deep, contextual conversation between human ingenuity and the specific, unyielding demands of the Earth itself. The future of earthquake-resistant design is already taking shape in laboratories and on construction sites, and it looks surprisingly familiar. We are entering an era of hybrid architecture, where the deep wisdom of the past is being fused with the precision tools of the present. This is not about abandoning steel and concrete, but about reinventing them. Material scientists, for instance, are creating a new generation of self-healing concrete. Inspired by the Roman recipe that used volcanic ash to grow stronger over centuries, these modern mixes are embedded with tiny capsules of healing agents or special bacteria. When a microcrack forms under stress, these capsules rupture, releasing a gel that hardens to seal the fissure, or the bacteria activate to produce limestone, effectively stitching the wound closed. This gives the concrete a kind of biological resilience, allowing it to recover from the small tremors that gradually weaken ordinary structures. It is a deliberate step away from the brittle perfection of modern cement and toward the living, adaptable quality of ancient mortars. The principles of controlled movement are also being re-engineered for the 21st century. Structural systems now incorporate flexible joints and damping devices that function like the sophisticated wooden brackets of a Japanese pagoda. Instead of rigidly welding beams, engineers design connections that allow a building to sway gracefully within safe limits. Some skyscrapers even use massive pendulum dampers at their peak, a high-tech echo of the suspended central pillar in a traditional pagoda. These are not added components fighting a rigid design. They are integral parts of a system designed from the ground up to move with rather than against seismic forces. Perhaps the most transformative development is digital fabrication. The complex, interlocking geometries of Inca stonework, which required a master mason's lifetime of skill to carve, can now be precisely modeled by computers and fabricated by robots. We can create concrete blocks with jigsaw puzzle edges that fit together perfectly, forming walls that behave like their ancient counterparts, shifting and settling during a quake before locking back into place. This technology allows us to replicate the seismic advantages of polygonal masonry at a scale and speed the ancients could never achieve, applying it to schools, hospitals, and apartment buildings. The most promising path forward is this synthesis. It is about using our computational power not to build more rigid fortresses, but to design intelligent, flexible systems that embody the time-tested principles of natural resilience. We can model the flow of forces through a building inspired by the golden ratio, or optimize the placement of modern flying buttresses to channel energy away from a glass tower. This hybrid approach represents the next evolution in our relationship with the dynamic Earth. We are learning to build with the ancient dancer's grace, using the tools of the modern world to create a truly resilient future, where our buildings are not just safe, but are enduring partners in the planet's eternal dance. Our journey through time reveals a humbling truth that true progress is not always a straight line forward. The silent, steadfast temples and pagodas are not just monuments to the past, they are enduring lectures in stone, teaching us that resilience is born from collaboration, not conquest. Our ancestors did not see the earth as an enemy to be subdued, but as a powerful partner to be understood and respected. They developed a sophisticated, intuitive engineering through patient, generational observation, learning directly from the land how to build structures that could move, flex, and dance with seismic forces. This was a wisdom etched not in blueprints but in the very culture of construction. We stand today with powerful technologies and deep scientific knowledge, capable of modeling stresses to the millimeter. Yet the evidence is undeniable. Our relentless pursuit of speed, uniformity, and cost efficiency has often come at the expense of the very durability that defined ancient mastery. We created buildings that are strong but brittle, predictable yet fragile. The challenge for our century is not to discard our modern tools, but to wield them with a newfound humility. We must fuse our computational power with the recovered wisdom of the past, creating a new hybrid architecture. Imagine cities where buildings are designed with the flexible joints of a pagoda, made from self-healing concrete inspired by Roman recipes and shaped by the harmonic proportions of sacred geometry. This is not a step backward but a vital evolution, a synthesis that honors both ancient insight and contemporary necessity. The stones of the past have whispered their secrets across the millennia. It is now our responsibility to listen, to learn, and to build a future that is not only safe but truly built to last.